Many people learning data structures come to believe that linked lists are more efficient because insertion is O1 compared to an array's ON. However, on real hardware, arrays are almost always significantly faster. Consider two pieces of code. Both have ON time complexity, so in theory, their performance should be similar. Yet when actually run, the linked list version is often orders of magnitude slower. Why is this? The answer lies in the low-level mechanics of how a CPU accesses memory. When the CPU reads from memory, it doesn't fetch just the 4 bytes being requested. It reads an entire cache line, typically 64 bytes. The elements of an array are stored contiguously in memory. For example, if an int occupies 4 bytes, a single 64-byte cache line can hold 16 consecutive ints. When the CPU reads array element 0, element 1 through 15 are loaded into the CPU cache along with it. Consequently, when the program subsequently iterates through array element 1 to 15, the CPU doesn't need to access slow main memory at all. It retrieves the data directly from the incredibly fast cache. In contrast, the nodes of a linked list are scattered arbitrarily throughout memory. Traversing a linked list means that each access to a node's next pointer jumps to a completely new memory address. This new address is almost certainly not present in the current cache line, which triggers a cache miss. When a cache miss occurs, the CPU cannot proceed with computation and must stall while it fetches the required data from main memory, a process that can consume over 200 CPU cycles. The process of traversing a linked list isn't really about the CPU computing. It's about the CPU waiting for data. With every step, it waits for a memory fetch. Traversing nodes can potentially cause n cache misses, causing the total time to skyrocket. So, in the real world, data layout matters more than time complexity. You're not just writing algorithmic logic. You are orchestrating how the CPU interacts with memory.